Okay, so let's have a look at the second question in the 2020 Higher Level Maths Leaving Cert paper 1. So what we have to do here is find two complex numbers z1 and z2 that satisfy the following simultaneous equations where I squared is minus 1. So I've identified the two equations here as equation 1 and equation 2. So if we just write down equation 1, which is I times z1 is equal to minus 4 plus 3I. Now what I'm going to do here is just divide both sides by this I here to get rid of it from the left hand side. So I'll end up with minus 4 plus 3I on the right hand side, all divided by I. Now the next thing I can do here is, because I'm dividing by a complex number, I'm dividing by this complex number here, what I need to do is multiply by the conjugate of that complex number over itself. This is really 0 plus I. What I'm going to do is multiply by minus I, 0 minus I over 0 minus I, or just minus I over minus I. So if I do that, I get Z1 is equal to minus times minus is plus, so I just end up with 4I plus 4I, and then minus 3I squared. On the bottom, I end up with 0 minus I squared. So what I end up with here is just Z1. Now Z1 here will be on the top here, the numerator becomes plus 4I, and the minus 3I squared, the I squared is minus 1, and minus 1 times minus 3 is plus 3. So really I just end up with 3 plus 4I. Now the minus I squared, well, that's just going to be minus times minus 1. Remember, I squared is minus 1. So we got minus minus 1, which is plus 1. So we're just dividing by plus 1. So our answer here for Z1 is just 3 plus 4I. 3 plus 4I. Okay, so what about Z2 then? Let's have a look at Z2. I'm going to use equation 2. So equation 2 is 3, let me use white here, so it's going to be 3 times Z1 minus Z2 is equal to 11 plus 17I. Now, we know what Z1 is, so I'm just going to put that in here. It's 3 plus 4I. 3 plus 4I is Z1. Minus Z2 is equal to 11 plus 17I. Let's multiply this out. We have 3 3s 9, plus 3 4s 12, minus Z2 is equal to 11 plus 17I. So what I'm going to do now is just take this part here and subtract both sides. Subtract this from both sides. So what I end up with on the left-hand side then is minus Z2. On the right-hand side, I end up with 11 minus 9, which is 2. And 17I minus 12I, which is plus 5I. Now we don't want minus Z2, we want plus Z2, so I've got to multiply both sides by minus 1. So we end up with minus 2 minus 5I as Z2. So this is my second complex number solution here to these two simultaneous equations. So I used simultaneous equation 1 here and 2 here. Okay, that's it for part A. Let's have a look at part B. In part B, we have the complex number 3 plus 2I, and we have the complex number 5 minus I. These are the first two terms of a geometric sequence. So find or the common ratio of the sequence. Write your answer in the form A plus BI, where A and B are integers. So our T1, our term number 1 here is 3 plus 2I. Our T2, term number 2 here, is 5 minus I. And we've got to find the common ratio. So the way you find the common ratio in geometric sequences is just to take any term and divide it by the previous term. So I'm going to take 5 minus I divided by 3 plus 2I. So this is just an exercise in division of complex numbers. So let's see how we do this. Well, as I stated in part A, the way you divide complex numbers is take the denominator, multiply by the conjugate over itself. So we're going to multiply by 3 minus 2i divided by 3 minus 2i. Okay, so let's multiply all that out. So we got to multiply the top by the top and the bottom by the bottom. So 3 5s, 15. And then we got minus 2 5s, 10i. Then we got minus times plus minus 3i. And then we've got plus, minus times minus is plus 2i squared. On the bottom then, same thing again, 3 3s, 9. And then we've got minus 2 3s, 6i. And then we should find we've got a plus 6i as well, which we do. And then finally we got a plus times minus, which is minus 2 2s, 4, and I squared. So if we do that on the top, we end up with 15 here, and it usually goes with this one here. So if we look at those two, we've got a, well, if we look at the one out at the end here, we have a plus 2i squared. Well, I squared is minus 1, so that plus 2 will become a minus 2. So we have 15 minus 2, which is 13. And then out here we have minus 10i minus 3i, which is minus 13i. On the bottom then we have 9 minus 4i squared. Well, the I squared is minus 1, so minus minus is plus, so that's really a plus 4. This is really a plus 4 here. So we got 9 plus 4, which is 13, so that's very handy. And then we have a minus 6i plus 6i, which will just give us 0. So we finally end up with 13 into 13, which is 1, minus 13 into minus 13, which is minus 1. So this here is our common ratio. And that's really it. That's it for part 1b. Okay, so let's have a look at part 2 then. So in part 2, we have to use de Moivre's theorem to find T9. So we've got to find T9. The ninth term in the sequence. Write your answer in the form a plus bi, where a and b are integers. So let's just write down T1 again and T2. So term number 1 was 3 plus 2i, and term number 2 was 5 minus I. And what we have to do is work our way out here until we find T9. Now we know that or here, or is 1 minus I think it was, wasn't it? Yeah, 1 minus I. So or here is 1 minus I. So what you could do is take, if you weren't asked to use de Moivre's theorem, what you could do is just take our term 1 and multiply it by 1 minus I until you got out here as far as T9. Now, because we were asked to use de Moivre's theorem, we can't do that. So we've got to think about it a little bit. So if we take term number 1 and we multiply it by 1 minus I, if we multiply it by or once, we get term 2. If we multiply it by or twice, we get T3. If we multiply it by or 3 times, we get T4. So therefore, if we multiply term number 1 by or 8 times, we'll get T9. So in other words, if we take term number 1, which is 3 plus 2i, and we multiply that by 1 minus I 8 times, or 1 minus I to the power of 8, that should give us term number 9. So this is where de Moivre's theorem comes in. So we're going to take 1 minus I, we're going to convert it into polar form, and then we're going to raise it to the power of 8, and then multiply our 3 plus 2i by that number. So let's take 1 minus I first and convert it into polar form. So first thing we're going to do is get the modulus of it. So that's just going to be the square root of 1 squared plus minus 1 squared. That will give us the square root of 2. So that's our or, if you like, our modulus. Now we've got to find the argument. So let's just draw a quick sketch here. So we can see that it's 1 minus I, so it's going to be in the fourth quadrant down here. Now, if you look at that, you're going out here a distance of 1, and down here a distance of 1. It's minus 1 really, but the absolute value is 1 here. Now, we have our reference angle here is alpha, and our theta, I'm going to use the positive version of theta. You can use the negative version if you want. I'm going to use the positive value here of theta. So let's work out what theta would be. Well, we can see here that the tan of alpha is just going to be 1 over 1, which is 1. So that means alpha is going to be the tan inverse of 1. So that gives us alpha as 45 degrees, or pi over 4. So that's our alpha. We don't want alpha, we want theta. So our theta then is going to be, you could use minus pi over 4. So you could just say this is minus pi over 4, which is fine. I'm going to use the positive value. So I can see that all the way around from here, all the way around to here is 2 pi, or in other words, 8 pi over 4. I want one less than that, so I want 7 pi over 4. So our theta is going to be 7 pi over 4. So theta here is just going to be 7 pi over 4. Okay, so now we have our modulus and argument. So that means then that our complex number, I'm running out of room here, so let's see, our complex number 1 minus I in polar form is going to be equal to the square root of 2 times cos theta, so it's cos 7 pi over 4 plus I sine 7 pi over 4. So let's just work out what that would be to the power of 8. So that means 1 minus I to the power of 8 is going to be all of this to the power of 8. So really what I'm doing here is I'm going to use de Moivre's theorem to do this. So that's going to be the square root of 2 to the power of 8. I'm bringing the 8 down. And then I've got cos 7/8 56 pi over 4 plus I sine 56 pi over 4. So what I've done really is just taken this entire right-hand side, raise it to the power of 8. So I brought the 8 down here, raise the root 2 to the power of 8. And then by de Moivre's theorem, I can take the 8 and bring it down here, and bring it down here, and just multiply the angle by 8. So that just gives us, let me see, we've got 1 minus I to the power of 8, which is equal to root 2 to the power of 8 is just 16. Now, the cos of 56 pi over 4, well, if you take 56 and divide it by 4, you get 14 pi. So we really end up with the cos of 14 pi here, plus I sine 14 pi here. Now, that's really 1 plus I to the power of 8 is equal to 16 cos. 14 pi is really 2 pi 7 times. So in other words, you go around, you start at 0, if you like, on the x-axis, and go around 2 pi, another 2 pi, another 2 pi. You're really going around 7 times. So really you end up back at 0 again. So really 14 pi is just 0. 0 pi, if you like. So we have cos of 0 and the sine of 0 here as well. Well, that just gives us 1 plus I to the power of 8 here is just going to be 16 times the cos of 0. The cos of 0 is just going to be 1, and the sine of 0 is going to be 0. So we just end up finally here, I'm running out of room here at the end, but we just end up with 16. So 1 plus I to the power of 8 is really just 16. So what were we asked to do? We were asked to use de Moivre's theorem to find T9, the ninth term of the sequence. So we know that term number 1 is 3 plus 2i. So I'm going to just do it over here. Just do it in here. So we have 3 plus 2i, and we want to multiply that by 16. So that will give us 48 plus 32i. And that's it. That's our term number 9. That's our 9th term.